Anna University, Chennai. He has carried out his postdoctoral research on anti-corrosive and fire-retardant polymer coatings at University of Minho, Portugal. He has also completed another postdoctoral research on topic of biocide loader polymers at De Montfort University, UK. He has great expertise in the field of polymer chemistry and material science and is meticulously involved in the research area of synthesis of nanohybrid coating and composites, fast epoxy hybrids, and an anti-fouling coatings for potential applications. Under his untiring guidance, 4 scholars have completed their doctoral degree and 5 scholars are pursuing their research work. In this juncture, I am proud to say that I also had a chance to complete my doctoral degree under his guidance. He is also acted as research supervisor for 50 ME and Tech students. He has 52 publications in Science Citations Indexed Journal published by the Royal Society of Chemistry, Russian Academy of Sciences, American Scientific Publishers, Wiley, Springer, Elsevier, and others. He has authored 8 books which have been published by Wiley, Springer, and CRC Press, USA, with an H-index score of 18 and I-10 index of 26. His publications have attracted 1,337 citations. Professor Dr. S. Anandakumar has successfully completed 5 major projects funded by various organizations like DST Nanomachines, Indo-Brazil Foundation DST, with a total grant of 70 lakhs. He is currently carrying out a project on EMI shielding polymers. He has been honored with the 5th National Award for Technology Innovation, CHIPAT, Government of India, year 2015. Active Research Award, Anna University, year 2014. Visiting Fellowship, European Commission Fellowship, year 2010. Visiting Research Fellowship, Royal Society of UK, DST of India, year 2004. Research Associateship, CSR India, year 2002. Extended Senior Research Fellowship, CSR India, year 2001. He has been an invitee for 41 lectures in various national and international conferences, symposium, faculty development programs, refresher courses, and short-term programs. He has also visited various countries like Portugal, UK, the Netherlands, Germany, and USA as a part of his research fellowship and invited lectures. Please join me in providing a hearty welcome to our invited speaker of this online FTP session once again. Thank you.
Thanks a lot for Saravanan for an elaborate introduction. And அனைவருக்கும் காலை வணக்கம்.
வணக்கம் sir.
Shall I now share the screen?
Yes, sir.
Yes, sir.
Saravanan sir, you stop.
Can you see my slides?
Yes, sir.
Yes, sir. It's clear, sir.
Yeah. So to begin with, I just want to start in Tamil. I don't mind. If you don't mind, I can say a few words from பாரதியார் கவிதை. So நல்லதோர் வீணை செய்தே அதை நலங்கட புழுதியில் எரிவதுண்டோ சொல்லடி சிவசக்தி வினை சுடர்மிகும் அறிவுடன் படைத்து விட்டாய் வல்லமை தாராயோ இந்த வையகம் பயனுற வாழ்வதற்கு. ஸோ இந்த ஜங்ஷன்ல இந்த பர்டிகுலர் பாரதியார் கவிதை வந்து நான் ரொம்ப முக்கியம்னு நினைக்கிறேன். பிகாஸ் இந்த பாரதியார் கவிதைக்கும் என்னோட டாக்குக்கும் நிறைய சம்பந்தம் இருக்கு. ஸோ ஐ ஜஸ்ட் தாட் ஐ ஷுட் ஷேர் this information with you. And whatever research that I've done so far, it's all because of my students, as vindicated by Dr. Saravanan, who's also one of the promising candidates who has done PhD under my supervision. So these are all my team members, without which the work whatever carried out in our lab would not have been possible. So Mr. Raju is presently working on bio-based corrosion prevention coating, and Mr. Sundar is working on bio-based films, Jochen Stanley is working on antimicrobial coating. Keithana, she is preparing a bioscaffold for 3D printing. And then Akin is presently developing a sensor, electrochemical sensor for pesticide removal. And Pavitra, who is presently working with carbon amino acid, she is supporting our research team by means of manuscript writing, and also she is contributing to our research team. Vanisri is working on natural biocomposites, and Ruth is working on waterborne coatings. And Pavitra, who is presently working with carbon amino acid, she is supporting our. I can't move to the next slide. I'm not able to move the next slide. Let me check. So this is one of the prestigious moments where I received an Active Researcher Award from the late Dr. Excellency APJ Kalam. This is given by Anna University. And the 5th Technology Innovation Award we received from Central Minister Dr. Anand Kumar. This was in the year 2015. So this is about my publications and all. And one of the books that I edited on eco-friendly nanohybrid materials for advanced engineering applications, which is edited, which came under CRC Press. And the main agenda of today's meeting, I'm going to talk about the background of the investigation. That is why I have chosen this particular area, because the title indicates strategic design engineering. So strategy, I mean, Tamil is vyugam. So strategy, what strategy that we have right now, so that we can realize the sustainable living. And I'm going to talk about materials that we developed in our group, and then objective of some of the works we did, and what are the materials that we have used to achieve the objective of the work, and finally research and discussion. It's I don't know why I'm not able to scroll down the slides. So sorry for the inconvenience.
No issue, sir.
Yeah, it's not going down. I don't know. Let me see. Okay. So since the topic talks about sustainability, I would like all the participants to know what is the exact meaning of sustainability. So sustainability means meeting the needs of the present generation without compromising the future generation. So that is what the sustainability means. And our environment, the world in which we live and work, is a mirror of our attitudes and expectations. And attitude decides our altitude. And why we have chosen this study? Because we know the recent past we have been hearing the tagline, say no to plastics. Plastics pollution cause it is very dangerous to the human being and all. We just want to see, is there any other alternative way of using plastics? That is why the conventional plastics, they cause a lot of harm to the environment, which cannot be resolved in a straightforward fashion. Therefore, if you want to realize the sustainable development and green economy, both require a brand new materials to avoid the occurrence of above problems. Therefore, natural polymers, biopolymers, and synthetic polymers based on annually renewable resources are the basis of the present century portfolio. We believe that these bio-based materials will gradually replace the currently existing family of oil-based polymers as they become cost and performance competitive. Sorry, again, it's a problem. I don't know what is happening.
So you can use the arrow key, sir.
Yeah, that's what I'm trying. I
working.
don't know. Suddenly, you know, it is getting jammed, and after some time only it is going.
You do not press escape button. See, sir.
Yeah, I did it. I did it, and still, you know, this same same status. Sorry for the inconvenience.
Yeah, yes.
So I didn't have this problem yesterday. I just checked everything yesterday. It worked well, but today I don't know why there is an issue.
I'll try to close this and restart, sir, with PPT.
Okay. So you want me to close it and then start it again, right?
Start fresh so that we can.
Okay, let me try. I'm just closing it. Yes, Saranam. Cursor vella vechirunuma. Oh, right. So I'm just opening it now. Okay. So need for bioplastics. So why do we need bioplastics? So bioplastics, actually they are classified into two types, bio-based plastics and biodegradable plastics. Generally biodegradable plastics meaning is that they can be degraded by the action of microorganisms, heat and moisture. And bio-based plastics. So these are all the different kinds of plastics in the recent past. They have attracted many researchers. So plastic products made by transforming bio-based material, either exclusively or in combination with the non-bio-based material. That is, you can have a combination of bio-based material and synthetic material. That combination can also be called as bio-based plastics. The exact meaning of bio-based material is one which has a significant portion of the carbon derived from renewable resources. So bio-based plastics carbon it is derived from renewable resources like corn, soybeans, grasses and other plant mass. Then apart from that, the biodegradable plastics, now the plastics products that are designed to break down for complete assimilation of microorganisms. In the polymer, whether it's a bio-based or non-bio-based, if they are capable of undergoing degradation under the action of microorganisms, then they are called as biodegradable plastics. Okay. So,
sir, your PPT is not visible, sir. Excuse me.
It's not visible.
Yes, sir. Yes, sir. It's not visible.
Is it now visible?
No, sir. Your desktop only visible, sir. PPT is not visible.
But I can see this. See this. I'm sharing my slide as well.
Slide is not visible.
Let me check. Is it visible now?
Yes, sir. Yes, sir. It's visible, sir.
Okay, sorry. Maybe this issue comes. Okay, right. So since the talk is on strategic engineering, as I told you, strategy means so எந்த ஒரு product, because we have seen that the conventional polymers have caused a lot of environmental pollution. Therefore, for making any product, for whether it is industrial purpose or academic purpose, we should have the following questions in mind. That is, what is the carbon footprint or profile of your product? In the product you make up பண்றீங்களோ and the product oda carbon footprint enna, adoda profile enna, you should have an idea. Then you have a mechanism of developing your own carbon footprint. Then you should have an idea about life cycle assessment. Life cycle assessment na ஒரு மெட்டீரியல் நீங்க வந்து எக்ஸ்ட்ராக்ட் பண்றீங்கன்னா எக்ஸ்ட்ராக்ட் பண்ணதுல இருந்து ஃபேக்டரிக்கு போகுது, ஃபேக்டரியில இருந்து it goes to cradle to grave, cradle to cradle. So all these things have to be understood thoroughly when you are making a product. And what are you doing to reduce products carbon footprint or profile? So நீங்க என்ன contribute பண்றீங்க environmental pollution க்கு by developing a product? What are you contributing? So that question also you should have in your mind. And you have to check whether you are moving towards a zero or neutral carbon footprint and total environmental footprint profile needed in addition to carbon footprint. So idu thavara environmental footprint you should have an eye on the environmental footprint. Only by checking all this above things, you can realize the sustainability. So sustainability it includes social impact and macroeconomics. It is not just like an environmental statement. And this slide will let you know why the carbon factor is very important. So as you can see from the graph from top to bottom, so it indicates the population growth, the water usage, the carbon dioxide concentration, the number of cars which have been used. So I have given data from 1750, from the year 1750 to 2000. As you can see, there is a steep increase in the population from 1925 to 2000. Same as the case with water usage, from 1900 to 2000, there's a steep increase in water usage. Similarly, the carbon dioxide emission also, it goes up, and the number of cars you started using is also, it is going up. So the ultimate objective of this present slide indicates the effect of carbon emission towards the environmental factor, so which in turn affects the sustainability of the ecosystem. Okay, so the other curve, it talks about the carbon emission by, which is called a Keeling curve, and again it indicates the intensity of carbon emission from 1960 to 2000. And statisticians believe it is a deceptive to say that there is a cooling trend is prevailing, but how far it is true, nobody knows, because there are a lot of protocols which are available. Phyto protocol, then you have US people coming up with their own protocol. So many protocols are coming, but the one has to keep in mind is why the carbon emission is going up. So it is because of the human activity. So from this slide, you can understand the amount of carbon which is emitted from the atmosphere and the amount of carbon that comes into Earth is maximum. And besides that, we also do some fossil fuel combustion, which also contributes for the carbon dioxide emission. And because of the greenhouse gases, it's pretty well that it is causing a lot of damage to the ecosystem, because the greenhouse gases, it forms a layer, insulating layer over the Earth's surface. As a result, what happens? The Earth will receive a lot of heat energy, and as a result, we are facing a lot of problems. So why I'm just emphasizing the importance? So we can try to reduce the carbon footprint by making a product which is going to emit less carbon dioxide. So that is the basic idea of this presentation. And when you look at the planet temperatures, so it's very important, you look into this. So the planet temperature, when you take Mercury, the planet which is very close to sun, so one would assume that it is burning surface because it is very close to sun and it is a burning one. And while the temperature on Mercury can reach up to 465 degrees, it can drop to minus 144 degrees centigrade. So there is such a big variation in Mercury's temperature because the planet has no atmosphere and it spins relatively slowly compared to some of the other planets. Similarly, the next planet, Venus, the second closest to planet to the Sun, has the highest average temperatures of any planet in our solar system, regularly reaching temperatures over 460. So Venus is so hot because of its proximity to the Sun. So Sun again, it has a thick atmosphere. The atmosphere contains a lot of carbon dioxide and sulfur dioxide. So this creates a strong greenhouse effect, trapping the sun's heat in the atmosphere and turning a planet into a furnace. So why I am just indicating the factors. We can no longer live in Mercury or Venus planet, which is because it doesn't support life. Whereas you take Earth, which is a planet in which we are living, it's a boon, I would say. So Earth is the third planet from the Sun. So for the only planet capable of supporting life. So the average temperature on Earth is 7.2 degrees centigrade, but it varies much more than at its extremes. The hottest temperature over recorded on Earth is 70.7 degrees, which is in Iran. Can you believe this? So the maximum temperatures went up to 70.7, and the lowest temperature was 89.2 degrees in Antarctica. So the main purpose why I'm just telling you the fact is Earth is a planet which supports living. So we'll have to keep the Earth in a conducive atmosphere. We have to keep Earth and do not pollute the environment so that we can have a very we can have a wonderful living, and we can also realize the sustainability. And Mars, and recent past, many people have started exploring Mars, and I read a lot of magazines where they even bought some places, some in Mars as well. But when you look at the Mars, it is a very cold planet, and its atmosphere to retain heat is relatively far from the sun because it is away from the sun. Therefore, it is very cold. Mars has an eccentric orbit around the sun, so it gets much closer at some times than others,
Sorry.
and its temperature can vary. Yes.
Sir, can you put full screen, sir? Slideshow.
Again,
Because,
slideshow. When I put what happens, you are not able to see it. That is it.
You can write.
Put it in.
Yeah, because it is visible in YouTube. Also, it is live streaming is going on. They find it difficult to see the slides because if you put slideshow, it will be better.
Custom. Shall I put custom slideshow?
Yes, sir. Is from. Sir, at the bottom, from this slide, you can put the bottom one.
Yeah.
No, sir. From current, sir, go to current slide. Go to current slide.
Click that.
Go to from current slide, sir.
Shall I put custom slideshow?
No, sir. Top. Next. No, sir. No, sir.
Next one.
From current slide.
Present.
No. Current slide.
Current slide.
Yes. Yes, sir.
Sorry.
For next screen, you can right click and put next. If you right click, you can go to the next slide.
Okay. Shall I go to next slide?
Yeah, sure, sir.
So as I told you, the carbon footprint, whatever product that you develop, you have to have an idea about the carbon footprint and the contributions made by carbon. You have to have an idea about it. So you need to understand the material or product carbon footprint. So which have a impact of replacing the fossil carbon with biocarbon. So that is the basis of this present investigation. So we thought of replacing the petroleum carbon with biocarbon. So process carbon footprint, it is nothing but it involves life cycle inventory analysis. So you have to understand the carbon emission from all stages of unit operation, then material balance and impact on the environment of the carbon emission, global warming potential. So this is about your process carbon footprint. Then environmental carbon footprint, it is nothing but life cycle analysis. So which includes carbon footprint plus other impact footprint categories like human health, ozone depletion, eutrophication, acidification, and photochemicals, fog as well. So when you look at the carbon footprint basics value proposition, so you see you get the polyethylene and polypropylene directly from oil, coal, natural gas, which is derived into naphtha, then it is converted into ethylene and polypropylene. At the same time, you can also get this ethylene polypropylene from crops and residues like corn and soya bean. So our idea is, why can't we synthesize ethylene and polyethylene from the corn that is available agricultural resources, which is going to give you the same ethylene and polypropylene. And from that, you get biomonomers, which are converted into polylactic acid and polyhydroxyalkanoates. Okay, so instead of getting polyethylene and polypropylene from crude oil, so why can't we synthesize the same ethylene, propylene, or polymers from agricultural crops? So that is going to eliminate the global warming scenario. So what is the impact of the material, that is product's carbon footprint on the environment? So when you look at it, 100 kg of polyethylene and biopolyethylene will result in net how many kgs of CO2 released into the atmosphere has to be taken into account. That is, a polyethylene I got it from petroleum resource, and the same polyethylene I am going to get from bioresource. So you need to compare the carbon emission made by these two polymers. So that should be calculated. Similarly, you can also calculate it for polyethylene terephthalate, which is commodity plastic. Many people you would have seen it in a household. So polyethylene terephthalate will have 2 carbon from glycol and 8 carbon from terephthalic acid. It results in how many net kgs of CO2 into the atmosphere. So when you look at it, it is very quite interesting. That is the polyethylene, which is obtained from fossil resources. 100 kgs of polyethylene usage will eliminate 314 kgs of CO2. 100 kgs of polyethylene usage will result in 314 kgs of CO2 emission. And polyethylene terephthalate, it's somewhere between 200 to 250. So 100 kgs of polyethylene terephthalate obtained from fossil resources is going to eliminate 240 kgs of carbon dioxide emission. Whereas the polyethylene, which is obtained from bioresources, it is not discharging any carbon footprint to the atmosphere. So, which is very interesting for the researchers. And that is one of the reasons why we started exploring bio-based polymeric materials for our research purpose. And this slide indicates the zero footprint product recycled, no release of gas to the environment when you are deriving polymers from bio-based crops or agricultural products or agricultural farm materials and all. So when you look at the global carbon cycling, the carbon management it takes place in the nature's way. So when you have carbon dioxide, after 1 year it is converted into biomass and agricultural products. These biomass and agricultural products will take 10 power 6 years to get converted into fossil fuel resources or petroleum or natural gas and coal. And from that, the chemical industries, through chemical industries, you can convert the fossil resources of petroleum, natural gas into polymers, chemicals, and fuels. Whereas these polymers and chemicals, they undergo degradation, and then again, they leave CO2 to the atmosphere, which is consuming between 1 to 10 years. So overall, when you look at the graph, it's a very time-consuming process. That is carbon dioxide to biomass, biomass to fossil fuel to polymers and chemicals. It's a very time-consuming process. And moreover, we understood that the polymer products which are obtained from fossil fuel is causing a lot of problem. So we thought, why can't we use this? So when you are avoiding the right-hand side process, that is biomass for fossil resources or petroleum, natural gas, instead of that, the biomass can straightaway be converted into polymers and chemicals without the process which I've indicated on the right. So that is what we have done. So we try to use the bio-based polymers. Thereby, the time consumed is very less, and also it is environmental friendly without causing any carbon discharge. So we have a new renewable carbon feedstock and an old fossil carbon feedstock. So I would prefer to have a new renewable carbon feedstock for our product making. And keeping this in mind, and many companies have now started using bio-based products, which is already available in the market. As you can see, the PET bottle, which is now available as a bio-PET bottle, so which I've indicated in the slide, it is made up of bio-based PET, so which can be degraded at a certain period of time after it is being used. So this is the strategy which we are thinking about. So instead of using a petroleum-based material, we thought of using a bio-based material, where we try to get the starting materials from crops and residues. We get biomonomers, then ethanol is converted into ethylene, and ethylene into corresponding polymer. So this is the strategy. So when you do so, what happens? What is the advantages of using this bio-based carbon replacing the fossil fuel is? When you have a bio-PET, 37.5 million metric tons of PET, if you are using, it is going to stop 17.2 million metric tons of CO2. That is because you are avoiding carbon dioxide emission to the atmosphere. So replace the conventional PET bottles with the bio-based PET bottles. So that could be a strategy that we are going to, we may think in the future. And it's a question of time, because as far as US is concerned, they have started using it. Maybe in India it takes its own time. And there are companies, a lot of companies in India who are selling this bio-based materials. So finally, ultimately, you can save 40 million barrels of oil per year when you are switching over to bio-based plastics. And when you look at the difference between non-carbon renewable fuels and biocarbon renewable fuels, and I would prefer the bio-based one than the non-carbon renewable fuels. As I told you, many companies have already started using this bio-based polymers. So Walmart is one who just who came out with a new product, and he has replaced all of your fossil carbon with biocarbon. As a result, they were able to save the energy. And you can see the estimated energy savings are equal to 800,000 gallons of gasoline in a year. And similarly, they were avoiding the elimination of greenhouse gases, which is equivalent to eliminating the CO2 emission from driving a car 23 million kilometers in a year. So greenhouse gas reduction is the second part of their messaging, despite lower US consumer awareness. Because if you create awareness about this bio-based plastics, I'm sure that we'll be able to eliminate the carbon dioxide emission to the atmosphere. So it opens up a lot of research avenues. So the bio-based plastics is really, it is coming up like anything. So based on this, so moving to the above reasons that I mentioned, keeping all the above ideas in mind, we have developed a certain materials using bio-based polymers, and we found some industrial use for the products that we made in our laboratory. So one of them is we were able to make a bio-based scaffold. So the scaffold, which is made by one of my students, Ms. Keetana, she is working on drug delivery. So she has made a bio-based breast implant, which can be impregnated with the drug and which can be put into a patient's body for cancer treatment. So the developed three-dimensional scaffolds can certainly be used as an implant material for the replacement of breast tissues. So the beauty of this technique is whenever a patient is suffering from breast cancer, so what we can do is to simply impregnate this drug-loaded breast into their body. So what happens after some time, because it is drug-loaded, drug is getting released into the atmosphere, it cures your tumor. And not only that, the cells can be grown automatically. So it's a self-healing effect can be realized by means of this bio-based material. Since the bio-based material is biocompatible, it is not going to cause any harm to the human being. And again, we thought of exploring this bio-based material for our coating application, because Dr. Saravanan was mentioning that our major research area involves anti-fouling coating and protective coatings. We thought, why can't we use natural materials into coating system? Accordingly, we have developed a biocide encapsulated nanozeolite. That is nanozeolite, it's a nanomaterial having porous structure. So what we did is we have incorporated a naturally available material like neem oil and chapaka leaves into the pores of nanogelites. And the nanogelites are further surface modified and brought into the epoxy monomer. And then we did the polymerization of nano containers containing this natural additives like neem oil and champaka leaves, which are available in India. And neem oil and champaka leaves, they have been in use in India for more than 5,000 years. So what is the ultimate objective or the advantages of using such natural coating materials? It is going to eliminate the undesired contamination. It will have low toxicity to human being and other target organisms. And it is no mutagenic, because the detrimental effect of mutagenic effect in the case of COVID-19. The COVID-19 is because of it is getting mutated. The virus is getting mutated, and that is why it is unpredictable. So that problem can be avoided using this strategy, and sufficient stability against UV and weathering, and it is long lasting. So durability is more. And this is another interesting project and product we made in our campus. Actually, it's a serendipity invention, I would say. Just we were walking in the campus of Anna University, we could see this fruit, which is nothing but a Stercula foetida. Its biological name is Stercula foetida. And we could see some fiber is getting out of this surface. So we thought, why can't we extract the fibers from the fruit and then reinforce it with a matrix? So accordingly, what we did, we just processed this fruit, we extracted the fiber, and then we reinforced the fiber to the matrix. We made a composite. And to our pleasant surprise, one of our students and our team won Best Paper Award in the international conference that held in Anna University in the year 2017. So why I'm just indicating, just not projecting myself, why I'm indicating is there are plenty of natural products available. Earth has given a lot of natural products to us. So it is up to us to explore the natural products, understand its, the values and the properties, so that you can explore it accordingly. So this is one of the materials that we developed in our laboratory. We made a Stercula foetida reinforced PLA and epoxy biocomposites. And similarly, we have also used spirulina. Spirulina, it's algae, sea algae, which has got a lot of antioxidant property, antibacterial property, antiviral property as well. So we thought, why can't we use it as a additive for PLA? So because most of the PLA, what happens, it undergoes degradation. But when PLA is used for packaging application, it has to maintain its low biodegradability. That rate should be low. So we thought of incorporating this spirulina and guava leaves. And to our surprise, what happened? The barrier properties have gone up. When we have incorporated spirulina and guava leaves into PLA, we made a film out of it. And the film is capable of offering better set of thermal properties, mechanical properties, and barrier properties ideally required for industrial applications. So we were able to make some products out of it, and the products were found to be very stable as well as very robust and high performance. And from the IR, we took the IR and we understand there is a good interaction between the biocide and our PLA. There is a shift in the vibration frequency that took place, and the carbonyl peak of PLA is getting reduced when the interaction is going up. And we also did antibacterial studies, and we found the combination, that is guava leaves and spirulina, they were offering very good antibacterial effect as well. And similarly, since PLA has found a lot of application, we thought of incorporating some inorganic pigments, because as I told you, the bio-based polymers are nothing but it's a combination of synthetic polymer and bio-based polymer, where the maximum portion is bio-based polymer only. So I have 90% of bio-based polymer, whereas I can go up to 10% of synthetic material. So keeping that in our mind, we started incorporating an inorganic pigment which is capable of reflecting the IR radiation and resisting the UV radiation. So we have made an anti-reflection coating using such inorganic pigments. We made a film out of it, and we have studied the properties, chemical properties, their interactions by means of FTIR, and we have calculated their mechanical strength, and they are found to be very effective. And this work was carried out by one of my students, whose name is Mr. Jogan Stanley. This work we did it during lockdown. And the basic idea of this work is, why can't we develop an antiviral coating? So we found that shift-based compounds are able to offer antiviral properties. So keeping that on our mind, we thought of incorporating shift-based into the moiety of PLA. So we understand there is a chemical interaction that is possible between shift-based compounds and PLA. So we made a wonderful film, antibacterial coating and antiviral test. We thought of sending this antiviral film to virology department, and the results we will come to know maybe after a month's time. Right now, what we understood is these films are capable of offering antibacterial properties. And another fascinating work carried out by one of my students, Mr. Sundar, who is presently working with the ITC company. So what he did is he has collected a peanut shell. So he has carried out pyrolysis, and he was able to get peanut shell carbon, which has got better set of properties, better mechanical properties, water resistance, contact angle is more, and carb value is less. So he is working in a abrasive industry actually. So the abrasive, abrasives are basically used for cutting and grinding operations. Most of the abrasives used nowadays are based on synthetic polymers. So what happens? The abrasive coatings, when they are applied on paper, what happens? The paper becomes non-degradable, because paper is a degradable material, but when it is applied with a abrasive coating, the paper becomes non-degradable. So that poses a lot of environmental threat. It contributes to solid, waste management. Therefore, we wanted to eliminate this. So we just replaced the synthetic resin with bioresin. So we have replaced PLA as a coating material for craft paper with the incorporation of this peanut shell carbon, and we were able to make some excellent products which offers mechanical strength, then barrier property, which is ideally required for making coated abrasive products. And similarly, we started incorporating zirconium oxide nano materials, and we want to study the nano influencing effect of zirconium oxide towards PLA. And this work we saw from ACS publication, and it's a very simple, straightforward technique. So why I'm showing this slide is, you need not depend on sophisticated instrumentations or techniques. There are cases, because in future we are going to have situations like pandemic and all. So we cannot go and get our samples analyzed in very sophisticated lab. So which is very much possible within our own lab itself. So this carbon nanotubes we are able to synthesize in our laboratory using beakers and sonicators. Nothing else is required. You don't. Yesterday I had an opportunity to listen to the presentation given by Mr. Ram. I think he was talking about this plasma, where he was telling the atmosphere plasma can also be made in the laboratory. So in a similar fashion, we also did this experiment, and we synthesized the carbon nanotubes. All we need to have is a nucleating site, which is nothing but a silica powder, on which we were able to grow carbon nanotubes of ferrocene and paraxylene. Paraxylene and ferrocene is a carbon source, and your silica nanoparticle is a nucleating site. So we were able to get this carbon nanotubes. The carbon nanotube synthesized in a laboratory is further, it is reinforced with PLA, and we made a film out of it. So surprisingly, when we took the IR, we were not getting any signals, any vibration frequency. Later, we understood that the carbon nanotubes were used for EMI shielding, and that resulted in sending a project proposal to DRDO, which was funded in the year 2017. So this PLA, carbon nanotube reinforced PLA, finds application in electronic field, like your cell phone. Most probably, many people can be seen with cell phone only. So what happens? The cell phone, the radiation that comes out of cell phone is very toxic to the human being. So if the cell phone covers are made using this particular material, probably we can prevent ourselves from toxic radiation. So this is another product that we made in our laboratory. Similarly, we were able to make some transparent films by changing the silica content. We were able to obtain completely transparent material to completely opaque material. So this is also carried out in our laboratory. And the recent past, we have published our findings in one of the reputed journals, Progress in Organic Coatings, which is in Web of Science, whose impact factor is 3.6. So this is the work carried out by myself and my student, Mr. Sundar, and Pavitra and Ghosh. This work is in collaboration with the Carbonundum Unisol. Now, Carbonundum Unisol is thinking of changing over to bio-based polymers instead of synthetic-based polymers. And another thing is, we were able to develop some, as I told you, we were able to develop some biocide loaded films. And this biocide is very interesting. It's a very proprietary item, so I don't want to name the biocide. And the biocide has got some acid, which has got sanapic acid, which has got a lot of properties like antibacterial, antiviral, anti-HIV, and all the properties are exhibited by this particular acid, which is present in a biocide. We have incorporated that biocide and we have made a film. And similarly, we have also incorporated organically modified monomer-methyl. So why we have done this is because PLA is a very good polymer, but though it has got some advantageous properties, the main problem with PLA is it doesn't have enough mechanical strength and thermal stability, and it is very brittle as well. So toughness has to be increased. So these demerits prevent the usage of PLA for industrial application. That is why many people are using PLA for domestic application. Nobody is willing to use PLA for industrial application. So we thought, why can't we modify the properties of PLA in such a way that it can be used for industrial application? So that is the reason why we started incorporating materials like organically modified monomer clay and this natural biocide. So this is about PLA. Why PLA we have chosen is it is the forerunner in the market, and it has got very attractive properties like renewability, biocompatibility, processability, energy saving, and it can be obtained by simple methods like lingopring polymerization and polycondensation. And it is available in different chiral forms like PLLA, PDLA, and PDLLA. And you can have different crystalline PLA, that is PLA containing less than 2% crystallinity, PLA which is crystalline more than 20%. We have a semi-crystalline PLA. So we have variety of PLAs available in the market, which can be chosen according to the end use application. Okay, so this is the life cycle, the cycle of PLA in nature. So what we do is PLA, which is made into product which undergoes degradation to carbon dioxide water, and the carbon dioxide water from photosynthesis is converted into agricultural product which undergoes degradation to starch on further hydrolysis and fermentation, which is forming lactic acid on polymerization giving polylactic acid. So as I told you, these are all the drawbacks of PLA. That's why we wanted to overcome the drawbacks by incorporating organic, inorganic hybrid materials into PLA. So this is the properties of PLA that we have used in our study. And then the materials, it's a very simple method which can be done in a laboratory. So you don't have to depend on very sophisticated equipments and all. So which can be tried in a lab, ordinary lab, which can be tried. So what we did is we have incorporated monomorlanite into PLA, and then we did the surface modification of monomorlanite, because monomorlanite is an inorganic phase, PLA is an organic phase. Obviously, there is no interaction between these two. So we thought of surface functionalizing the monomorlanite. We did the surface functionalization. Accordingly, the reaction went up well. Similarly, we have used biocide as well. As I told you, why we have used biocide into PLA is because biocide can offer antibacterial property, anti-diabetic property, phytochemical property, immunity improver, anti-cancer, anti-HIV drugs. So that is why we thought of using such biocides into the system. And this is the solvents that I have tried with PLA. And the ideal solvent for PLA could be ethyl acetate, ethyl alcohol, because we don't want to use chlorinated solvent. And that's why we preferred using ethyl acetate and ethanol. And rarest of rare cases, we have used chloroform, which is very rare. And this is how the films were made. And we did the thermal studies. And as you can see, the ethyl acetate and chloroform, in which the PLA forms an excellent film. And we did the mechanical, that is the strain curve. As you can see, the green one, which indicates PLA 100% and then 2% of monomorlanite. So as we reinforce only 2% of organically modified monomer, we were able to observe phenomenal improvement in mechanical properties. Same as the case with thermal properties. As you can see, the thermal properties are getting improved for the 2% OMMT clay loaded PLA nanocomposite materials. And we did the XRD study as well, and we can see the polymer form is an intercalated nanocomposite. Intercalation is a process where the polymer chains get infiltrated into clay galleries. So the 2 theta value is getting reduced as we keep on increasing the percentage of non-morlanite clay. So this is the concluding remark we obtained from our study. So we optimize the percentage of OMMT into PLA is 2%. The surface morphology we studied by SEM, which indicates the surface roughness, which is very much required for your fracture toughness. So we understand the PLA, it is no longer brittle when it is loaded with the organically modified monomer, it becomes tough and stiff as well. And it is able to offer better set of mechanical properties which are needed by industries. Similarly, we made a PLA biocide films using the biocide, the proprietary biocide which I indicated. As I told you, the main ingredient of biocide is phenolic acid, and the PLA, the structure of PLA is indicated down. And we found there is a chemical interaction between these two. And we were able to optimize the percentage of biocide in PLA. It is 5%. 5% of biocide in PLA exhibits better set of properties. So and we can see the 5% of biocide is able to improve the mechanical strength to a greater extent with elongation at break as well. So normally it is very difficult. Now material scientists are actually they are looking for material which will have both stiffness and toughness. So this is a state of the art. So from our study, what we understand is we were able to develop a material which is having both stiffness and toughness. So that's the novelty of your research work. And then we did hardness tests. We did the water absorption test. So on all the cases, the PLA with the 5% biocide is able to offer better set of properties. And then we understand the interaction between biocide and the PLA. And you can see the neat PLA, the characteristic peak of neat PLA is due to the carbonyl peak, which comes around 17-14 centimeter inverse. And the 57 centimeter inverse due to the methylene present in PLA. So when we observe the PLA and biocide, the black one corresponds to biocide, whereas green one corresponds to neat PLA. Blue one is PLA with the 10% biocide loaded, and red one is PLA with the 5B. So what happens here is the neat biocide, that is biocide itself, is capable of forming hydrogen bond at peak, which is indicated by a broad peak. So when the biocide is incorporated with PLA, the hydrogen bond at peak is getting decreased. So the decrease in hydrogen bond at peak is the indication of the biocide is having interaction with the PLA. And based on that, we found the following observations. The presence of broad peak, as I told you, around 3,500 corresponds to biocide. A sharp peak around 1,650 indicates the presence of alpha beta unsaturated ketone present in biocide. And two peaks around 2,850, 2,800 from neat PLA indicate the symmetric and asymmetric stretching of CH3. The disappearance of broad peak of biocide after PLA combination indicates the phenolic acid is having an interaction with the PLA. So this is also explained by the decrease in OH as we add biocide, and the intensity is getting decreased. As you can see, the OH peak intensity is getting decreased as it is getting interacted with the PLA. And its thermal stability is also found to be high. Though the initial degradation temperature is low for the biocide loaded system, however, the high temperature resistance is found to be higher in the case of PLA with a 5% biocide loaded system. Similarly, we did the antibacterial study, and we were able to see our films are very active against gram positive and gram negative species. We did the fungal studies. As I told you, some of this work we carried out during lockdown because we cannot afford to have a virology department or antibacterial lab. So what we did is we thought of using whatever that is available with our house. So we thought of using bread and the mold and yeast. So in that environment we placed our film, and we were able to observe antibacterial effect of the our system. And finally we did the soil burial test, because we wanted to make sure even after the incorporation of inorganic material and organic biocide, we don't want our PLA to lose its original biodegradable behavior. So we did the soil burial test accordingly, and we found that the biocide loaded and the inorganic system loaded PLA, it is having a slight low degradation rate. However, it degrades at a later point of time. So the neat PLA undergoes degradation very fastly, whereas the hybrid PLA system, they do undergo degradation, but at a slower rate. But still, they are capable of undergoing degradation. So we made sure that we don't compromise with the biodegradable behavior of our products. So this is the conclusion. So PLA films, we made it using biocide, and it is obtained, which is we observed the interaction with the FTIR and TGA, and we measure the hardness. And finally, we concluded from the study that PLA with the 5% biocide is the most ideal system for packaging applications. And similarly, the present work we are carrying out in our lab is we wanted to use, because as I told you, most of the industrial applications, they use halogenated solvents, which is very toxic to the environment. And as I told you, the basic idea of my presentation is strategic designing. So what is the strategy that is required so that we can have minimum pollution? That is the basic idea of our research work. So we thought of eliminating the halogen-based solvents, and we want to replace it with a non-halogenated solvent. Accordingly, we have made non-halogenated solvent incorporated PLA systems, and then we did the DSE studies because the time is almost it is done, I guess. So we could understand that PLA having 10% of PEG is able to form an excellent film. Beyond 10% of PEG, it forms phase separation, and accordingly we get a different melting point. That melting point corresponds to the melting point of PEG. And then we made a film out of this. We got excellent oil resistance as well. So this product, as I told you, this product, now it is being tried by industries. Carborundum Universal is now trying to use this product instead of the synthetic polymer based coated abrasives. And they were able to observe the modified PLA craft coated abrasive is able to offer better set of properties, let water absorption, and they exhibit excellent oil resistance, which is ideally required for industrial this thing. And this is other applications which people can think of. You can make biodegradable porous polylactic acid film as separated for supercapacitor. Yesterday, actually, there was a mention about supercapacitor, which are ideally required for space application, because in space and all, you cannot carry batteries which will involve weight, because space nowadays, they wanted lightweight material with very high strength. Therefore, in space, you can have the capacitors in the form of foils. So plastic foils can be used as a capacitor, whereas you can make some capacitor using PLA-based, bio-based polymers. And we can also think of making corrosion prevention coatings. And some of them have already started working. This work, we got it from the Science Direct, and some of them have made a spin coating, and they found the material is able to offer high corrosion resistance. So you can also think of bio-based coating materials. And then you can also make flexible membrane, polylactic acid flexible membrane for, you can use it for various electronic applications. Actually, for transport, it is possible. And it can be used for various high performance engineering applications as well. So these are all the references. And thank you for your patient listening. Thanks a lot. Any questions? You're most welcome.
Sir, one more question.
Yeah. Yes, madam, proceed.
Yeah.
Hello.
Radha ma'am is asking, who is under YouTube live stream, is any work in biocide?
Yeah.
Against
Before that, let me not forget, thanking the organizers. let me just read the name. Dr. Nandini Devi from Department of Chemistry, head of the department, and B. Saravanan Suresh. And then one more person, let me read. and Punita for giving this opportunity.
Thank you, sir.
And sorry
Shall
for the
we go with
inconvenience.
the questions, sir?
Yeah, tell me, madam, what is your question? You please tell me.
Is any work in biocide locust insects for using agricultural fields?
Actually, presently in our lab, we are working for biocides, natural biocides, having the properties that I've indicated. We wanted to explore this for various engineering applications, man. Maybe we can try, give it a try for your purpose as well. Because whatever material that I've indicated, even the Stercula foetida is capable of offering antibacterial, antioxidant properties. Presently in our lab, we are working for biocides, natural biocides, having the properties that I've indicated. We wanted to explore this for various engineering applications. Maybe we can try, give it a try for your purposes. Because whatever material that I've indicated, even the Stercula foetida is capable of offering antibacterial, antioxidant properties.
Sir, one more question.
Yes, please.
Asked by Tirupati Assistant
How
Professor,
many
Department
months?
of Physics. Yes. How many months or years taken for PLA biodegradable?
As I've indicated in the slide, PLA will get degraded within 180 days. It will get degraded. And we were able to show that even after the incorporation of additives, the PLA retains its biodegradable nature.
How many months or years taken for PLA biodegradable?
180 days means 6 months. As I've indicated in the slide, PLA will get degraded within 180 days.
One more question, sir.
Yes, madam.
What solvents can help make a PLA gel stable at
Ethyl acetate and ethanol could be an ideal solvent, madam. Because it's a non-halogenated solvent, and ethyl acetate works very well. And some of our students are working further, to make films, wonderful films. Right now, as of now, we found ethyl acetate is an ideal solvent.
what solvents
Sir, one more question.
Yes.
What kind of coupling agents should be improve the interference between PLA and glass fibers?
Because it's a non-halogenated solvent. I don't get your point. Can you repeat the question again?
Yes, sir, I will. What kind of coupling agent should to improve the interface between PLA and glass fibers?
You can try POS. POS, I think Saravanan, you may be knowing it. POS is an excellent, because one of our papers, we found POS is acting as a coupling agent that we published in silicon. So they can use, since it is a polylactide, epoxy terminated POS can be tried. I guess epoxy and PLA will have interaction.
So,
and amine coupling agents, gamma glycidoxypropyl triepoxysilane, any silane coupling agents can work.
So one more question.
Yes.
Why does graphene not change PLA tensile properties?
Graphene, we have not worked. We worked on carbon nanotube. In fact, we are trying to work on graphene. So we worked on CNT. So we have not explored graphene. So none of my slides show graphene. So we did work on CNT, and we found that CNT is offering this EMI shielding. That's why when we took the IR, we don't get any signal. So that was very interesting to us.
Okay, so one more
that
question.
That made me to use this film for yes.
Though which technique the films are being made up by your student? I repeat, though which technique the films are being made by your students?
Yes, exactly. They optimized the process parameters. They made wonderful films. And initially there was some issue. Actually, we were not getting proper films. They were brittle, or it is getting broken and all. Now we have a mechanism of making wonderful films. And one of my students, Mr. Sundar, what he did is he made a solvent and PLA composition where 25% of PLA can be dissolved. Actually, for industry, the maximum percentage of PLA which can be dissolved is only 10%. Whereas our students, they were able to dissolve 25% weight of PLA in a solvent.
So a question
Okay,
from
sir.
Mr. Shanmugam.
Yeah.
Is this biocides are used for implant materials, bone replacement techniques?
Exactly,
Can
because
we?
you know they can try. That's what I told you. I've indicated the properties of biocide, antiviral, anti-HIV, antibacterial properties. So why can't? And since they are natural origin, they are not going to cause any harm to the body as well. And the
Uh,
polymer is biodegradable as well, biocompatible as well. So you can very well try. Obviously, you can try.
Another question from the same person.
Yeah.
What type of technique they are using to make films?
Solvent casting technique, and then doctor's blade. They have another technique called doctor's blade. They apply a coating on a tile. They leave it, and then they apply also a coating on the paper, leave it for some time, allow the solvent to evaporate, then it leaves a film on it. Then you can simply, by application of the pressure, you can remove the film, and then you can test it. It's a very
Fine.
simple method. And that's why, I just want to focus the simple method so that everybody can try in their lab. And
Fine.
in fact, the carbon nanotube synthesis, it's very possible, which we did it in our lab. It doesn't require any sophisticated equipment. All we
Another
need is
question.
a sonicator and beakers.
A question from Dr. Peter Amaldas.
Yeah,
Biosynthesized silver nanoparticles, citizen nanocomposites.
yeah.
How to improve the filming forming nature? Any input, sir?
Yeah, we need to first impregnate the biosynthesized silver nanoparticles into a corresponding bio-based polymer. See whether you are able to form any homogeneous mixture or not. Otherwise, we have to understand the surface chemistry. So you need to understand the surface energy, adhesion, thermodynamic work of addition. All these factors have to be taken into consideration and see the permutation and combinations, and then change the surface chemistry, surface energy. So normally the interaction between solid and liquid will be more when the surface energy of solid is more and surface energy of liquid is less. If this criteria is meet, then you will have a proper homogeneous mixing. So surface energy plays a major role.
Fine, sir.
So
Okay,
surface
sir.
energy includes a lot of interaction. That is induced dipole interaction, hydrogen bonding, covalent bonding, ionic bonding. All these forces have to be taken into consideration for understanding the surface interaction.
Okay, sir. Thank you, sir. Thank you so much, sir.
Any other question? I'm sorry for the inconvenience that caused because I'm not a technical guy. So I'm a
No
chemist.
issues, sir. No issues.
No issues, no
So I'm a
issues.
chemist. I'm extremely
Thank you, sir.
sorry. I hope I just entertained you, I guess.
So
I
very
enjoyed
nice
this
and
session. It's
informative
very
talk,
less.
sir.
Thank you, sir.
So thank you very much again, once again, for the opportunity given by the St. Joseph management, and special thanks to my student, Saravanan, without which, it is not possible. So thank you, Saravanan. Thank you.
Thank
Thanks a
you.
Thank you.
lot.
Thank you, sir.
Thank you,
Thank
sir.
you.
Thank you
And
so much,
your
sir.
chemistry department, you're doing an excellent job. So keep doing it.
Thank you, sir.
Thank you very much.
Herewith, we are concluding our morning session. Thank you one and all once again. Please join us in the afternoon session by 2:30. Thank you once again.
Thank you.